Okay, there we go. All right, so we are taking the minimum of a particular set. So now the next question is, what is in that set, right? So everything in that set, is a subprimum of yet another set. So now it is important to bind the variables n and k so that they make sense. Because we're reading from the outside in, so the first thing we do is to bind the value of n. N only has one single requirement. It has to be greater than or equal to 0. I mean, it kind of implies that it has to be an integer, I guess. So n has to be an integer that is greater than or equal to 0. So once we know that n is just an integer, basically it's a non-negative integer, okay? But it can be any one of those. So once we fix the value of one particular n, then we can look into k, because what we're doing here is we're taking the supremum of yet another set. So supremum and infimum, they both work on sets. So in this case, supremum is working on the set, which is starting from this curly brace and ending with this curly brace over here. So we can see, we are basically taking a subset of the sequence of x, or we are taking a subsequence, not a subset, but we are considering elements of a subsequence of x, where the index of x is k, and then k only has to be greater than or equal to n. So that means we are taking the supremum. The supremum set is the set that where we are taking the supremum would consist of xn, xn plus 1, xn plus 2, xn plus 3, and so on. And it keeps going and going. Okay. So the next line is just an expanded version of what is displayed here. Is basically saying we are just taking the supremum of x of k, where k is greater than or equal to 0. And then the next one is when k is greater than or equal to 1, and then when k is greater than or equal to 2. And then we take all of these supremum. There's an infinite number of these things, and then we take the infimum of the set of all of the supremums. In a sense, we are taking the minimum of maximums. But the maximum, each one, is starting with a particular element of the sequence, and it goes all the way forward until just keep going and going. Okay. So are we clear on this concept for now, or are there any questions about this notation? Yeah, we could do an example, but it's hard to actually visualize because n is supposed to approach infinity, and each one of these is supposed to kind of keep going too. So I suppose we can do something like this. Just give me a second here to set it up. So we'll go ahead and use a spreadsheet. And then what we'll do is we are going to use one column for I, which is the index. So the index is okay, yeah, it converted lowercase I to uppercase I because I forgot to turn off the auto correction, which is under tools, and I think it's under customize. Nope, it's probably the next one. Alright, so I guess index I. There we go. Nope, it still capitalizes the I because it thinks it is referring to self. I as in myself. Alright, let's see if I can turn that off using options. And nope, it's not this one. I can't remember how to turn off the auto correction in LibreOffice Calc. Well, I guess I can just say this is I, and then the next column is going to be x subscript of I. I'm trying to think of a way so that it's the oscillation will settle at some point of time, and I think I just got it. All right, so we can do it this way. So it's going to be the all right, so the base is going to be based on -1, but I also want to make sure that it has another component that changes the amplitude of the oscillation. So we're going to add okay, we'll do a 5 divided by this number plus 1, because we don't want a division by 0, so it has to start with at least 1. So when this sequence goes further and further, it's going to be the contribution of 5 divided by something plus 1, that's going to be smaller and smaller, because A2 will get larger and larger. Okay, so we want to change the addition to a subtraction so that they lean in the same direction. That doesn't seem right. Oh, it's actually okay, because alright, so we'll do one more change here. Alright, so I intentionally defined a function where it is oscillating, and the oscillating is actually going to increase because I'm not decreasing the amplitude part sufficiently. Oh, okay, I know what to do. Alright, so we are just going to change the amplitude by using this portion, and then the other side is just changing the amplification, the amplitude of the oscillation. So that should make it a little bit easier to deal with. Alright, so let's see how this works out. There we go. So that's good. Alright, and we don't need the precision that is being used here, so we'll go ahead and limit the number format to have 2 places after the decimal point. So we can see how okay, let's go ahead and make this a little bit larger. So in the actual definition, this I, which is represented by column A, basically just goes on and on and on. But in our example, it is not going on and on and on, because we cannot have an infinitely large spreadsheet. So it's just a crude visualization of the concept that we are dealing with here. So over here in column C, we are going to say we are going to take the let's look at the definition. So we're going to take the maximum of everything from index I and up. So this is basically the maximum or the supremum starting from index 0. Okay, so it's from x subscript of I and all the way up to the end of the sequence. So in this case, we do have an end of the sequence because you cannot have an infinitely large spreadsheet. But in the case of the actual theory, the sequence just keeps on and on and on. So now we can say this is because max is a real function in the spreadsheet, so we can just go ahead and use max here. So it's going to take the maximum of let's see, it's going to be B2 and all the way down to the last one in the sequence. So that would be 188. So I have to type $188 because otherwise the end is going to float as I make copies of that cell. So now, if I just keep going like this all the way to the end, I suppose I could have just double clicked all the way to the end. but I didn't. So there we go. All right. So is this part okay? Does everybody understand how column C is, what column C is representing? Column B? Sure. So column B is having the first portion is just controlling, what the sign, whether it's negative or -1 or 1. And then the second portion controls the amplitude. So it's basically just 5 divided by 1 plus, 0, 1, 2, 3, 4, and so on. So the amplitude is going to decrease as I increases. And then the sign just keeps flipping between 1 and -1. Is that okay? All right, cool. All right, so, oh, you're welcome. All right, so now we want to look at the infimum, the limit superior. Sorry, we look at the limit superior. So the limit superior, there's only one, okay? Because the limit superior is taking the minimum of all the maximums. So now this becomes the minimum of this entire thing. So it goes from C2 all the way to C188. And that becomes, well, it's close to 0, because it's never really 0 itself, because we cannot make this spreadsheet infinitely large. But you can kind of imagine that if we make the spreadsheet larger and larger, column B is going to become smaller and smaller, but it will keep oscillating until it becomes closer and closer to 0. Now, this way, if I define a function like this, the limit superior and the limit inferior would be the same. They're going to be 0. Okay. In other words, if the index, keeps go on and on and on and on, then eventually, xi will be very closer and closer and closer to 0 from both ends. So it's going to oscillate between positive and negative, but the magnitude is going to get smaller and smaller, which means the limit of this sequence is actually defined. So now what I'll do is I am going to make it so that that does not happen. So the amplitude, in addition to the portion that varies depending on I, there's always a +1. In other words, the magnitude is not going to settle down and get closer and closer to 0. It will always, basically be between 1 and -1. So, because I made that change, you can see how the sequence itself is basically alternating between two numbers that are, one is close to 1 and the other one is close to -1, but it's not going to settle to 1. But we can also see, when we take the maximum of the sequence starting with index 0, starting with index 1, starting with index 2, we have 6, and then we have 1.0267, and then we have 2.66, then we have 1.027, and so on. So we can see how column C is starting to converge. Okay, I'm going to use the word converge very loosely, but it's starting to converge. It's not oscillating as much as before anymore by the time we get here. And then when we take the limit superior, this is the limit superior up to index 188, but remember, in the actual definition here, it keeps going. Okay, there's no upper bound for n and there's no upper bound for k. They should just keep going. So is that helpful, Liu? In terms of illustrating, the concept of limit superior. Okay, very good. So we can kind of imagine limit inferior is kind of the same thing, except, where we take the maximum, it would take the minimum, and then when we take the minimum, it would take the maximum. So in this case, the limit inferior, up to 188, or index 188, is going to be -1.26, blah, 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 okay? But they are converging. Now, the other way to look at this is to look at it from a graph perspective. Excuse me. So if I plot a graph, Okay, now remember this is also, it will give you the idea of what we're talking about, but it's not going to be exactly the same as in the definition, because in the definition the index I goes, all it keeps going. But in this example, we do have to end at some point, so it doesn't work the same way. So we're going to use an XY chart, and I suppose we can use points only, because otherwise it might look a little bit too busy. And there we go. Nope, this is not the entire graph. The entire graph. Let me scroll down a little bit here. This is the graph. So basically, it just keeps oscillating between these two. Maybe I can change the graph. The chart type, so that we actually have lines. Then you can see the oscillation. But it'll be quite busy. All right. So instead of using points only, we're gonna use just lines. And instead of using straight line, we can use smooth. There we go. And you can, it's really busy because we're fitting 189 points within, a very small region in terms of the area. But you can see how it keeps oscillating. So in this case, it would not have the sequence itself doesn't have a limit. But we have a limit superior, which is basically sort of 1, and then we have a limit inferior, which is sort of -1. In other words, as the sequence keeps going and going, we can identify an envelope, okay, that contains the oscillation itself. And as long as that envelope, seems to be quote unquote stabilizing as the index goes, further and further, it will still have a limit. It will still have a limit superior, which is the upper bound portion, which is kind of like if you look at this curve here, this is sort of the upper, the limit superior, and then this is sort of the limit inferior. It's not exactly, because when you look at the actual value in the spreadsheet, that's not. It, this gives you the exact, what we see here. This is our supremum, and then this is the infimum of the supremums. All right, so do we have any questions? That was a good question. I wouldn't have shown you guys, a kind of illustration, of the concept. But that concept works for limit superior and also limit inferior. So are we good so far? Are we understanding the definition of limit superior and the definition of limit inferior? All right, cool. So now we move on to the concept of an upper bound. So when we talk about these, starting from section 3.6 and all the way to the end, we are going to have two functions. One is called f, the other one is called g. And by the way, this g function has nothing, absolutely nothing, to do with the out of no discussion function g. So when we have these two, okay, we are basically trying to compare, quote unquote, compare two functions, function g and function f. And what we are doing here is the big O notation, interestingly, is going to be, it returns a set, okay? So when we apply the big O notation to g of n, it is giving you a set of functions. And in this case, how do we define that set of functions? F of n is an element of big O of g of n if and only if, when you take the limit superior of the absolute value of f of n divided by g of n, it is not infinity. That's it. That's the entire definition. Okay. So when you look at this definition, it goes like, all right. So let's think about this absolute value thing here. That's the first thing. So the absolute value thing is here, just so that we don't have to worry about negative values. Okay. But we are still looking at the ratio. Okay, we are still looking at f of n divided by g of n. So, okay, Alright, so we don't have to worry about negative values because we are taking the absolute value of the division between f of n and g of n. So then the next question is, what can be something that is less than infinity? Well, just about any real number. Okay, if you pick any real number, as in a number, it is less than infinity. You can pick a really, really, really big number, like 2 billion. Okay, 2 billion is fine. It is less than infinity. So the only one thing that is not less than infinity is infinity itself. Okay, so as long as the ratio between f of n divided by g of n is as n approaches infinity, as long as that ratio is not infinity, we are still fine. Is that okay? As long as it settles down, we are still okay, and in that case, f of n would still be considered an element of big O of g of n. Alright, so let's use some examples, okay? Because this kind of definition of big O is probably a little bit foreign, because when we use, or when other classes use the big O notation, we are just going like, oh, this is the order of magnitude, or this is the complexity order, but not quite in this sense, okay? So we'll go ahead and use a few examples. I'm just looking around to find my notepad. Alright, there we go. And we are going to start a new tab. There we go. Okay, so now we're going to define some function for f and then some function for g, and then see what happens with the limit superior as n approaches infinity. Okay, so that's what we're going to do now. So let's go ahead and define something that's simple. Okay, so let's define f of n to be just n itself. We'll define g of n also as just n itself. So now the question is, in this case, is f of n an element of big O of g of n? So I'll ask the question here, in big O of g of n, question mark. Alright, so we look at this and go like, let's check it, right? Because all we need to do is to plug in f of n and g of n over here, and then we just have to think about what happens when n approaches infinity as we try to figure out the limit superior. So in this case, so the first thing is we want to find the sequence first, okay? So when we define the sequence, x of I is basically just, the same thing as f of, by the way, I need to change this a little bit because otherwise we'll have division by 0. So I'm just going to add 1 to it so that we don't end up with division by 0. So we'll define x of I to be f of I divided by g of I. Okay, so in this case, when we expand the definition of f and g, we just end up with n plus 1 divided by n plus 1. Whereas n goes, I, not n. This is I, and this is also I. Whereas I starts from 0. So x underscore 0 is what? Okay, I'll get you guys to think about this, okay? Can someone tell me what is x underscore 0? Underscore, come on. There we go. So what happens when I equals to 0 when we evaluate this thing? Come on, you guys can do this. No. No. 0 plus 1 is 1, right? So we have 1 divided by 1. There we go. Alright. So as a trick question, I'm going to ask what is x underscore 1? Woohoo, yes. So they're all 1s, right? No, they're not 0. None of them is going to be 0 because we are dividing, the numerator and the denominator are the same no matter what I is. Okay, as long as I is greater than or equal to 0 as an integer, the result of the division is always going to be 1. Exactly. I cannot be -1 because the index of the sequence has to start from 0, or implicitly it's starting from 0. Typically, what n is a problem size, so it is basically the number of elements in an array, the number of records in a file, and so on and so forth. So they don't go negative. So now, correct. Yeah, but since we put a restriction of I, must start from 0 as an integer or as a counting number, so we don't have to deal with the situation when I equals the -1. Okay, all right. So the what about the limit superior? I mean, let's plug this in, right? So we're talking about the x as a sequence is really just 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 all the way, right? It's they're all ones. So now if we think about the limit superior, of n approaching to infinity, and we want to look at the sequence x of I, okay, x of n, what do you think that is going to be? The limit superior, and when n approaches infinity of x of n, what do you think that's going to look like? Okay, let's plug this into the definition that we talked about earlier, right? So this is the infinimum of a set where each item in the set is by itself the supremum of the set, and this one is x underscore k, where k is greater than or equal to n, and then this one is where n is greater than or equal to 0. That is what we are dealing with here, okay? And loosely, we are talking about the minimum of a bunch of maximums, right? So we're looking at the minimum of the maximum, and then we have xk. So the indexes stay exactly the same, like so. So now we look at this and go like, okay, let's solve for all the maximums first, right? What do we have here? What is the maximum of x of k as for all k's that are greater than or equal to n? And we'll start with n being 0 first. Okay, so n is 0. So what do you think is the maximum of 1, 1, 1, 1, 1, 1, 1, 1? Just 1, right? What about the maximum of x underscore 1, x underscore 2, x underscore 3, and so on? In other words, this one is the maximum of all of these ones. And then this one here is the maximum of all of these ones, everything except for the first one. And then this one here is the maximum of all of these ones except the first two. And then this one is the maximum of all of the ones except for the first three, and so on. So we can see that, oh, this is silly. This is just silly because that's just one. All right. So is that answering the question? Because the original question is f of n as a function in the big O of g of n? What do you think? Look at the requirement. In order for that membership to happen, is we want the limit superior of f of n divided by g of n, and then the absolute value of that thing, to be less than infinity. Do you think 1 is less than infinity? Of course it is, right? And since 1 is less than infinity, then we go like, oh, okay. So in this case, f of n is an element of big O of g of n. So that seems to be pretty easy. Let's try another example. So we'll try another example where f of n is defined to be just n, and then g of n is defined to be n plus 1 the whole thing squared. Okay, there we go. So now we look at this and go like, this time is going to be a little bit different, right? Okay, so we look at the sequence, which is x underscore I, x subscript I, is now going to be defined as the absolute value is not important because both f of n and g of n are guaranteed to be non-negative when n is itself is non-negative. So we don't have to worry about taking the absolute value. So we just go ahead and do the division. So this is f of n divided by g of n. So that turns out to be basically n divided by n plus 1, and then the denominator has its own square. Okay. So this is how we are defining x of I. I keep using n, but I really should be using I here because I is the index into the sequence. So I should be used in all of these places. So this is how we define x underscore I. So we'll look at x underscore 0. So x underscore 0 using this definition is 0 divided by 1 squared, which is really just 0 because 0 divided by anything that is non-zero, is defined and it is just 0 itself. What about x underscore 1? Well, that's 1 divided by 2 squared, which is 1/4. X underscore 2 is going to be 1 divided by 3 squared, which is 1 divided by 9, and so on, right? So now we look at this and we say, okay, let's go find the limit superior. So now we look at the lim sup as n approaches infinity of x of n. Okay. Oh, right, you're right. Okay, so Anita is correct. I forgot about the numerator is just I itself, so it should be 2. That is correct. Thank you, Anita. Alright, so now we look at this and go like, I wonder what that is going to be. So now we apply the original definition. So we have limit superior of a bunch of stuff. And then each thing that is inside the set where we're taking the not limit inferior. This is actually just infimum. Okay, we're taking the infimum of a set, and then each item in the set where we're taking the infimum is going to be a supremum of something, and it is, this is based on n. N is greater than or equal to 0, and then over here we have we have x of k where k is greater than or equal to n. So now we look at this and go like, I wonder what it's going to look like. So now we just we try to solve for one of these supremum. So we'll try to solve for the supremum when n equals to 0. So we're looking at the supremum of x underscore k where k is greater than or equal to 0. I mean, this is one of the items that we have to solve, and there's a whole bunch of other things, but we want to focus on one thing at a time here. Alright, so can someone tell me what this particular value is going to be? We are starting from the beginning of the sequence, and we are saying, well, we want to find the maximum from the very beginning of the entire sequence when k as the index is 0. But we'll go all the way to the case when as k log gets larger and larger. K just keeps going larger and larger. So what do you think this number is going to be? And remember, we are taking the maximum in this case. What do you think that's going to look like? Well, just look at these 3 numbers that we have already worked out. So of these 3, which one is the maximum? The 1/4 is going to be the maximum of these 3, right? So now the question is, what do you think is going to be the next one? X underscore 3 is 3 divided by 4 squared, and that's going to be 3 divided by 16, right? So now, just looking at this particular trend, do you think any element that is after x underscore 3 can potentially be greater than or equal to 1/4? Nope. Okay, so that means 1/4 is going to be the answer to this one, right? So now we have infinitum of 1/4. What about the next one, when k is greater than or equal to 1? Well, that's 1/4 too. And because this is a set, we only get one of them in here. What about the case when k is greater than or equal to 2? Well, that's going to be 2/9. What about the case when k is greater than or equal to 3? That's going to be 3/16, and so on, right? So basically, eventually, we end up with finding the infimum of 1/4, 2/9, 3/16, 4/25, blah blah blah. Keep going, right? And what do you think is the infimum of all of these numbers? Remember, this is a set that has an infinite number of elements. So the question is, what do you think is going to be the quote-unquote minimum of all of these? What do you think looks like the trend? Exactly, the trend is they're all getting down to 0. There we go. All right. So now that we have solved the limit superior of the division or the quotient between f of n and g of n, and we know it is 0, the next question is to ask, well, it's kind of stupid, but we still have to ask that question. Is 0 less than infinity? The answer is yes. 0 is in fact less than infinity, maybe. So 0 is less than infinity, and as a result, n as a function is in the big O of n plus 1 squared. Okay? So this is really kind of odd, because you would think, okay, f of n is saying something is just proportional. G of n is sort of, you can look at it, when n gets really large, you just look at it as n squared, okay? So we are now saying, if the actual time complexity of an algorithm is linear, we can still say it is big O of n squared. That's basically what we are saying. That is what we are saying here, which is counterintuitive, because when you encounter the big O notation, okay, I think probably in one of the classes that introduce sorting or searching. Okay. All right. So let me put this in even more plain terms. Okay. So now we can say linear search, okay, of an array of n items is in big O, the time complexity, okay, I should say, the time complexity of linear search of an array of n items is in big O of n squared. You go like, really? Yes. Okay. So the bottom line is big O is looking at an upper bound of the time complexity of an algorithm. So when we use the word upper bound, it doesn't have to be a tight bound. It can be a very unreasonable upper bound. Okay, I can give you an analogy. If I ask, of the same age, okay, of the same age, I would let me ask you a question that seems to be kind of like, we kind of have to think about it. So I'll ask you the average weight, okay, of a chimpanzee versus the average weight of a person of the same phase of their life. Okay, so we're taking into consideration, the total lifespan and blah blah blah. Okay, so comparably, if we look at a teen chimpanzee versus a teen human, who's heavier? And you go like, the chimpanzee is going to be a little bit lighter, and the human's going to be, heavier. And then the next question is, what about a gorilla? So gorillas are actually quite a bit more massive than humans. So you go like, yeah, the gorilla wins in this case. So at the same phase in life, okay, a gorilla is going to be heavier than a human. So then I keep going and make this more absurd. Okay, so at one point I'm gonna ask you, what about elephants? At the same phase of life, okay, teen, middle age, old, okay, almost dying, okay. So at the same phase of life, is an elephant heavier than a human? You go like, of course it's gonna be heavier than a human. That's basically what we're dealing with, okay. It is just an upper bound. We are basically asking, is G an upper bound of F? That's all we are asking. It doesn't have to be a tight bound. So n squared is a tight bound of n. So is n cubed. So is n to the power of 4th. Okay, so is n factorial. All of those are upper bounds of, just linear, which is n itself. So big O doesn't tell you a whole lot. Which also means, in many contexts, you probably have seen people using the big O notation in the wrong way. Alright, Angel is typing something. I'm pretty sure that's gonna be good. Alright. You can, it's an upper bound, so it depends on it also depends on where you live. I traveled to a very small town in Oregon once, and when I order something from Amazon, without changing the delivery address, it says, yeah, we can do this in a day or two or something like that. And then as soon as I update my address to the actual address, in Oregon, it goes like, it's going to be 4 days now. So it depends on where you live. That is not a guaranteed time. But the important part is we're looking at an upper bound. And the next one talks about negligible. So we're still looking at stuff here, but this one is just taking the limit of a sequence. And basically it says, if f of n divided by g of n as n approaches infinity, if this becomes 0, then g of n, it is a negligible. It means g of n is a gross overestimate of f of n when the ratio approaches 0. That kind of makes sense, right? Because if f of n is just n and g of n is n squared, and n starts with 1 so that we can avoid the division by 0 problem, then it meets this requirement. So that means f of n in this case is just n itself, g of n is n squared. So we can now say n as a linear function is an element of the gross overestimate set of n squared. In other words, n squared is grossly overestimating n. That's basically the bottom line. Now the little o notation is not used a lot. Okay, it's very seldom that you will find a reference to the little o notation because it's not very useful. Because basically little o is a subset of big O, because big O is just asking one thing: is it an overestimate? Is it an upper bound? Not overestimate. Is it an upper bound? That's what big O is saying. Okay, if one thing is the upper bound of something else, then big O applies. Little o, on the other hand, is more restrictive because it's asking, is it a gross overestimate? If it is a gross overestimate, it is automatically an upper bound. So everything that is in little o is also in big O, but not the other way around. But little o, or negligible, the term negligible is not used a lot because we don't need a gross overestimate of time complexity because we want it to be as tight as possible. The next one is lower bound. So lower bound is almost the same thing. It uses it uses the Greek letter omega again. So this is, I think, the third time we see big omega being used in this class. The first time we saw omega was the set of all the operators or connectives when we talked about propositional logic. The second time is when we look at the outcome set of experiments, and specifically in the homework assignment when we talk about permutations. Okay, so that's the second time we look at omega. This is the third time, and this is completely independent to the other two omegas. Well, we only have 26 letters in English, and Greek is not a whole lot better, right? So, gotta recycle at some point. So this omega which has nothing to do with the definition of omega in the other two contexts where we use the Greek letter omega. This one is just asking whether in this case G is a lower bound of f. Okay, so the other one is upper bound, this one is lower bound. So how do we know something is a lower bound? Well, as long as the ratio of f of n divided by g of n is not 0 after you take the absolute value, as long as it is not 0, then it is a lower bound. G of n is a lower bound of f of n. That's it. I mean, it's as simple as that. So what happens when f of n is growing faster than g of n, so that this limit inferior is actually going to be infinity? Well, then the question is infinity greater than 0? Well, infinity is greater than 0, so yes. In those cases, it would not meet this requirement. It would meet this requirement, so the g of n is a lower bound of f of n. So are we still good? Are we still understanding, upper bound versus lower bound? If you compare those two, you can see how similar they are. Because one is looking at limit superior, the other one is looking at limit inferior, and that's it. And then one is comparing to see whether the limit superior is less than infinity. Basically, is it a constant? Okay, is it a particular constant? That's what this is asking. The other one is asking, is it greater than 0? As long as it is not 0, it would meet the requirement of g being a lower bound of f of n. Alright? So omega is also not really used a lot when you read literature of algorithms, because we are usually not interested in the lower bound of the time complexity of an algorithm. If I tell you, okay, I have a really awful, okay, let's think about a really, really awful search algorithm. It's called random search. And the idea is I will sit in a tight loop, and then for each iteration, I'll just randomly pick a number, and that number is a valid index into an array. And in other words, I'm just picking a random element in each iteration to compare to. I don't even bother to say, well, if we have used a particular index already, let's not use the same index. I'm just going to say, let's just pick a random index. As long as the index is valid, we'll use it. So in that case, what is the lower bound of that algorithm of confirming an element is actually in the array? The lower bound is going to be a constant time algorithm. Just in case we are so lucky that the first time we go through the algorithm, it just picked the right index already. So it's constant time. The lower bound of that random index search algorithm is constant time. It is big. It's omega of 1. So now the question is, well, is that lower bound useful? Does it mean anything useful to you? The answer is no. The answer is no, because I don't need to know the best case or the lower bound of that search algorithm. I want to know the upper bound, where it is basically the upper bound is infinity, because it is possible that the upper bound, I should say, the upper bound is infinity, because it is possible that you never really get to the element or the index of the element that you want to find. Even if the element is in the array, there is always that chance that every single iteration does not use the index of the element of the value that you want to search for, you want to look for. So that's why lower bound is usually not very useful. So just as, okay, Aiden has something to say, I'm gonna wait. N times the harmonic of sum of n. I'm not familiar with what is the harmonic sum of something, so. Oh, okay. Yep. Alright. So now, just as there's a negligible, to upper bound, there's a dominant to lower bound. So, basically dominant means it is a gross underestimate of f of n. That's basically what it is. Not really useful. It uses the sign, the symbol of lowercase omega, but you don't really see that a lot because it's not very useful. Now, what is useful is tight bound. Okay, if we can find the tight bound of the time complexity of an algorithm, that's what we want. So now we want to find out, but what does it mean, when we use big theta? So big theta is basically saying if f of n is in the big theta of g of n, it just means that g of n is both the upper bound when we use the big O, and also a lower bound when we use the big omega of f of n. In other words, when g of n is both the upper bound and the lower bound of f of n, then we use the symbol of big omega, which basically means it is a tight bound. G of n is a tight bound of f of n. Any questions about upper bound, lower bound, tight bound, gross overestimate, gross underestimate, and so on? Alright, so tight bound means limit goes to a finite or specific element. Nope, tight bound is, okay, tight bound is basically just saying it is both, g of n is both a lower bound and an upper bound of f of n. So that means when you plug in f and g, it would meet this requirement. The limit inferior has to be greater than 0, but at the same time the limit superior also has to be less than infinity. So now you have to think about this, okay? It has to be less than infinity, which means it cannot be infinity, and yet it has to be greater than 0. So what is left in between? It has to be a constant. That's all. Okay, it's basically just saying that the limit superior has to be a constant. The limit inferior also has to be a constant that is not 0. That makes it a tight bound. That makes G a tight bound of F. So when we use the word tight bound, we are not applying to a specific element. We are applying to the limit behavior of the entire sequence. Angel is typing something, so I'm gonna wait a little bit. Alright, so the question is, are all tight bound sequences, do they have linear complexity in that case since it's a constant? Nope, it's okay. Let me give you an example of a tight bound. Here we go. So let's take f as f of n is n plus 2 to the power of 2. Okay? and then we'll look at g of n as just n squared. And then we say n is greater than or equal to 1 so that we don't have to deal with the division by 0 thing. Okay, so now we may look at when we look at the limit limit superior first. Okay, let's look at the limit superior first of this particular set. Okay, so the set would be, and then we define, oh, okay, I know exactly what to say here. So this is going to be the absolute value. Now, I'm going to let go of the absolute value because f of n is non-negative and then g of n is also non-negative. So there's no need to specify the absolute value thing. So now we just say, we are looking at the limit superior of a set, and this particular set has basically f of 0 divided by g of 0, f of 1 divided by g of 1, f of 2 divided by g of 2. Oh, okay, I forgot. N has to be greater than or equal to 1, so this one cannot be in the set. There we go. Alright, so we are looking at f of 3 divided by g of 3, and this is a sequence, not a set. So this is a sequence, and so on. Okay. Alright, so when you think about the limit superior of this thing, we now apply the actual definition of limit superior. So limit superior is the infimum of a set, and then each item in the infimum is a supremum of another set. And I'm just going to borrow the same definition from the beginning. So this is n greater than or equal to 1 in this case, and then this one is x. Oh no, I would say x f of k divided by g of k, where k is greater than or equal to n. Alright, so this is the full expansion of what we're dealing with here. So what do you think this infimum, this limit superior is going to look like? Just think about it. Okay, if you just substitute 1 into here and 1 into here, you basically just get alright, so we'll spell out a few terms just so that we have real numbers to work with. So when n equals to 1, then we have 9 divided by 1. When n equals to 2, we have 16 divided by 4. When n equals to 3, we have 25 divided by 9. When n equals to 4, we have 36 divided by 16, and so on. So if I ask you, what do you think is... Yep, Aiden's got it. It's just 1. In this case, the sequence actually has a limit. Okay, in other words, we didn't actually have to use limit superior. But when in the case there is a limit, then the limit is the same as the limit superior and also the limit inferior. So that's kind of the bottom line of this whole thing. Okay, so what about the limit inferior of exactly the same thing? Okay, so I'm just going to copy and paste. Alright. So the limit inferior of the same sequence is going to be 1 as well. So now we look at these things and go like, hey, the sequence actually has a limit because it approaches a single value. There's no oscillation whatsoever. It just goes and down to one particular value. So in this case, it is obvious that 1 is less than infinity. It is also obvious that 1 is greater than 0. So that's why f of n is an element of big O of g of n when we define f of n as n plus 2 to the power of 2 and g of n as n to the power of 2. Then someone's going to say, okay, let's make this more complex. Let's make this so that we add the log of n. Okay, I'm just using natural log, but it doesn't really matter because it's just a ratio in this case. So what do you think? What do you guys think? Would it change the membership of f of n versus big O of g of n? The answer is, oh, okay, this is log of n. There we go. Big, yeah, it's the natural log of n, which converges to a particular value really soon. So Jack is correct. Okay, Jack is correct that even when f of n looks kind of ugly like this, and you can make it look even uglier, by saying, oh, by the way, we also have 1 divided by n plus 2. Okay, that is not going to change anything because um, the portion that contributes to the growth of f of n the most is n squared. The n squared is the n squared component inside n plus 2, the whole thing squared. That it determines that when n gets larger and larger, as n approaches infinity, it really is the same as g of n. The rest of the components become insignificant as n approaches infinity. All right. Yeah, that would do it too. Because when you have sine and cosine, they're both bound between 0 and 1, so they cannot possibly contribute anything that useful when we already have a component of n squared. So tight bound is what we want. Okay, in other words, f of n. Okay, so let's take a step back. Okay, what does f of n typically look like? Okay, so f of n is what we don't want to actually figure out. Because f of n is going to be kind of really ugly, because we have to take those like, oh, the number of times we're going through the iteration is n, but the number of times we actually perform the comparison is n plus 1, because we need that one last comparison to exit a loop. So there's that kind of plus 1 that we don't, it's like, it just makes everything look so ugly. So f of n typically has a lot of quote unquote ugly components to it. So it typically, if we're talking about bubble sort, okay, if we're talking about a bubble sort, f of n is going to have one component that is the coefficient of n squared, another one that is the coefficient of n, and then there's one constant component, because you have to initialize everything at the beginning, and that's only done once. So f of n looks ugly. But g of n, on the other hand, is something that is clean and simple. So g of n typically is n squared. Is n. It can be 1, in the case of a constant time algorithm. It can be n times log n, which is the the theoretical limit of sorting algorithms, and so on. So g of n is usually a very simple thing, and then f of n is what we don't want to have to figure out, because it's going to look really ugly. So the idea is, we don't want to figure out f of n. We just want to know, does it belong to this family of functions? Does g of n, is g of n an upper bound? And then we have to ask the opposite question of, is g of n is a lower bound? If the same g of n is both, can be proven to be the upper bound and also the lower bound of some really ugly f of n that we don't want to figure out, then we just say, we'll just say f of n has a we just have to say that g of n is a tight bound of f of n, and we don't have to actually figure out f of n. That is the whole idea of behind order of magnitude, or the what most people refer to big O should have been big theta of an algorithm. Are we getting the general idea of why we need to understand big theta, and how big theta relies on big omega and also big O, and why we don't want to actually why we don't want to figure out f of n itself? We just want to know, whether we can use g of n as a tight bound. And once we know that g of n is a tight bound, we just go like, yeah, that's good enough. We don't have to worry about all the small coefficients for the components that really do not matter. Are we good? taking a look at the time, it is 108. So let's go check out a few algorithms just so that we can see whether Wikipedia is using the right notation or not. So we're gonna check out merge sort. Merge sort in Wikipedia. There we go. And we want to look up the time complexity. So worst case, we have a upper bound of n times log n. Best case, it has a lower bound of n times log n. And the average is big theta, which means the type bound is the upper bound and the lower bound for the average performance is n times log n. Yeah, so it does work. It does use the notations correctly. So now the next time you want to look up an algorithm, to find out okay, what is the time complexity of a particular algorithm, don't just look for big O, because big O is just an upper bound. It does not necessarily have to be a tight upper bound. In other words, in this case, if somebody is lazy and go like, yeah, I vaguely remember merge sort is better than bubble sort, I'm just going to say the worst case performance is big O of n squared. Technically, that person is not wrong. Because big O of n squared is still a valid upper bound of the worst case performance of merge sort. It's just not a tight bound, but it's still an upper bound. And the same person can look at the best case performance and go like, yeah, I'm pretty sure no sort algorithm can be better than a constant time algorithm. I'm just going to say it's big omega of 1. Well, that person technically is not wrong, because a constant time is an underestimate of the actual performance of merge sort. So we don't want to use big O or big omega by themselves. We want to use big theta if it is possible. All right. So I'm not gonna analyze the algorithms and explain why merge sort has a time complexity of big theta of n times log n. But I will give you this, okay? And you're gonna go like, really? So I'm gonna tell you that no sorting algorithm can have a time complexity better than big theta of n times log n. Or I should say big O of n log n is the best you can do with any sorting algorithm. I'm not going to give you the proof because I don't have it. But when you move on to a 4-year university, you will probably have to take a class called Introduction to the Analysis of Algorithms, or an Introduction to Algorithm Analysis. Okay, both basically they mean the same thing. And in that particular class, which is going to be pretty much a math class, not a really programming class, but a math class, the professor will teach you, how to find the actual tight bound of an algorithm. But more interestingly, in that class, the professor will probably also, explain to you why no linear, I shouldn't say linear, but why, okay, I'm looking for the right word, why in the case of an algorithm running on top of a deterministic machine, a sorting algorithm cannot have a time complexity better than n log n. Okay, so that's it. Okay, merge sort is pretty much as good as it can get. So are all of the other sorting algorithms that have the time complexity of the upper bound as n log n. I have to be careful of saying deterministic machines, because when we have non-deterministic machines, it's a different story. Because when you have a non-deterministic machine, you can basically spread out an infinite number of threads, where each thread is creating one permutation of the input, and the only thing it has to do is to check whether the resulting permutation is sorted or not. And it takes linear time to check whether a sequence is sorted or not. So in the case of a non-deterministic machine, the time complexity, it all depends on how quickly you can make a permutation out of a sequence. And I'm not talking about making all of the permutations like your homework assignment. I'm talking about just making one single permutation, and it should be a linear time thing. To make a permutation of a sequence is a linear time thing. Fun stuff. Well, Ivan is typing, so I'm pausing here. Alright, so the question is the human brain a non-deterministic machine? In the sense of Turing machines, it is not a non-deterministic machine, because a non-deterministic machine in Turing's machine sense means you can basically spin off a new thread whenever you feel like it. And that is not the case. Okay, if you think about okay, so if you think about all the states of all the molecules and all the things, all the physical stuff in your head, in your brain, as one single state, your brain only has a finite number of states. Okay. On the other hand, the brain is non-deterministic. Everything is non-deterministic in the sense of because of quantum physics. So when you look at a electron, okay, in its quote-unquote orbit, okay, so most of the time when people think about an electron orbiting around a nucleus, okay, the picture that most people think about is you have the nucleus in the center like Earth, and then you have the electron orbiting like the moon, like this, right? That picture is grossly incorrect, because first of all, the orbit of an electron is not really an orbit, on a plane. It is more like a surface, in three-dimensional space. And that surface doesn't even have to be contiguous. There are certain orbits where, one part of the orbit is up here, the other part of the orbit is down here. They are disconnected. The two portions are disconnected. But the electron does not actually move in the orbit. It basically transitions from one position to another position based on probability functions. So it just goes from one location and the next moment is somewhere else based on the probability function. So from that perspective, nothing is deterministic. Everything is probabilistic. Alright, so Garrett says, doesn't it phase in and phase out our plane of existence in a sense? I suppose you can look at it that way. I don't know whether that is how the physicists, would describe it. But we know it is not a continuous motion, when we look at the electron in quote-unquote orbit. It's all the probability thing. It's not exactly teleporting. I'm not really sure how to describe it. It just doesn't, the location is just not known. The other thing that's interesting, I know I'm just burning time because we only got 2 minutes left. I'm just burning time in this class. But it is interesting from the perspective of, what is going to happen when quantum computing becomes real. Okay, because everything that we know at this point about algorithms, they're all based on I wouldn't use the word deterministic, because deterministic versus non-deterministic has very specific meanings in computer science. So I'm going to be using probabilistic. Okay, so everything that we are talking about these days in a computer, they are not probabilistic. Okay, the transition is sure. Okay, we know 100%. Okay, from here we're going to end up here. If you add 1 to 1, you're going to get 2. Okay, so we know that for sure. But once we move into quantum computing, well, the whole idea of quantum computing is it doesn't work that way. So um, so that's one thing. For those of you who are interested, think about this problem. When you it's the wave thing, with the slit. Okay, let me show you what I mean by that. Okay, wave, slit, and quantum, and then we just look for an image. It's the double slit experiment. So look it up, because this is one of those things where, even though it's a very simple experiment, it does illustrate the idea of behind quantum mechanics in a very kind of really visible way. So I'll leave you guys to read this, but the idea is the question is, are electrons particles? Like, hey, here's one, here's another one, here's another one, here's another one, or is it a wave? Kind of like ripple, when you throw a little piece of rock into a completely flat surface of water, you can see the ripples propagating from where the rock lands. So the question is are electrons particles, or is it a wave? So that is kind of the kind of question that this experiment is trying to answer, because in some cases it seems to behave like a particle, but in some other cases, in the double slit experiment, it seems to behave more like a wave. The real answer, okay, I'm going to leave it up to you guys to read the answer. I'm not going to spoil the answer here, but the real answer is very interesting. It is not a wave, and yet it is not a particle. It is something that starts with a P. So I'll leave it up to you guys to read that. It is not relevant to this class entirely. Nope, not photon, not photon. Not photon. Because photon is the same way. Photon actually behaves the same way too. You can ask the question, is photon a particle? Something that you can count like one by one by one, or is it a wave? Well, the answer is it's actually neither. Okay, so I'm just gonna leave all of you guys hanging, with all of these questions in quantum mechanics. It's not exactly both. It is actually the third thing that kind of explains why sometimes it behaves like a particle and other times it behaves like a wave. And interestingly, that idea, also may apply to matter overall speaking. So that's, kind of a push to that concept. Yep. So for those of you who want to read up quantum mechanics, there's a lot of stuff. Okay, but the idea behind quantum mechanics, you don't have to understand all of the math stuff. It is the idea that is interesting. Yeah. Yeah. Well, remember, quantum mechanics, baffled Einstein. Einstein said, God does not play dice. And then Bohr goes like, well, according to my math, he does. and the disagreement between these two was what eventually led to quantum entanglement. The discovery of quantum entanglement, which is a phenomenon that is proven by physics, by experiments now, but at the time when Bohr and Einstein were arguing, they didn't have the means to conduct experiments to prove it one way or the other. So yeah, kind of interesting stuff. Not totally relevant to this class, but for those people who are curious, more stuff to look up over the weekend. Alrighty, so we are done with today's lecture. I will see you guys next Monday, and we do not have a homework assignment yet. And oh, by the way, read ahead of me. Read the graph theory module ahead of me. There's an algorithm in that thing, so you want to read ahead of me and try your best to understand the algorithm. And then on Monday, we'll go ahead and run that algorithm on paper so that I can illustrate how it works. All right, you guys have a nice weekend too. Thank you. All right, bye.